In this lesson, we're going to continue our study of testing hypotheses about proportions. So first, let's review an example that covers the stuff from the previous lesson. So if your feet don't match, is the right one more likely to be longer or shorter? It's a silly question, and I'm sure you're just dying to know the answer. Although, if you were a shoe manufacturer, and you may use this information to make one shoe just a hair bigger than the other. Just saying. So we took a sample. So we have students in a statistics class. They measured the lengths of their left and right feet to the nearest millimeter. The right and left foot measurements were equal for 103 of the 215 students, but the 2 foot lengths were different for the 112 other students. So we're going to consider these 112 students for whom the 2 measurements were different. Of these students, 63 had the longer right foot. So first step is find the sample proportion. So the sample proportion that had the longer right foot were 63 out of 112. So 0.5625. Next, tell me the null and alternative hypotheses. So, maybe the hypothesis is that the right foot is bigger, but I don't think in this one there's anything that says that's necessarily the case. So we're going to say that H naught is that the proportion whose right foot is longer is exactly 1/2. So half people have the longer right foot, half have the longer left foot. And HA, no direction specified, probability proportion is not 1/2. So summarize the data into an appropriate test statistic after first verifying that the necessary data conditions are met. So we need to check NP naught. So 112 times 0.5 is 56, so check that's good. And 1 minus P naught is going to be the same thing. (112) minus 0.5 times 0.5 as well is also 56. So yes, that's met. So our test statistic is our z-score, which is given by p hat minus p naught over standard error of p naught. So let's find the standard error of p naught. Well, that's root p naught, 1 minus p naught over n. So 0.5, 1 minus 0.5, or 0.5 over 112, which is 0.047246. So our z-score is given by our sample proportion, which is 0.5625 minus 0.5, all divided by that 0.047246, which is a z-value of 1.32, approximately. I did round that. So 1.32 standard deviations away, so you have 56% of these people have a longer right foot, but that's only 1.32 standard deviations away from your mean, which probably is not unusual. So find the p-value by comparing the test statistic to the possibilities expected if the null hypothesis were true. So what this means, with two-sided test, probability z is bigger than or equal to 1.32 or less than or equal to negative 1.32. Remember that from this picture, that's this kind of thing. So I'm going to do twice the probability that z is less than or equal to negative 1.32, which is 2 times 0.0934, or 0.1868. Decide whether the result is statistically significant. So if we take alpha equals 0.05, which is the typical level, the answer is no, because our p-value is bigger than alpha. And let's make a conclusion. So we fail to reject H naught. And that doesn't mean H naught is true, it just means there's insufficient evidence to say it's not. And that's how we're going to say this. There's insufficient evidence to conclude that one foot is always longer than the other. And if you look back at step D, you can see that even if we didn't do a two-sided test, we would have had a p-value of 0.0934 and we still would have failed to reject H naught. So don't go making one shoe bigger than the other quite yet. So the next unit talks about the differences in two population parameters. So we're going to be talking about one population parameter minus another. And the first thing I'd like to talk about is I would like some examples of situations in where you'd want to care about these two different proportions. And so here are mine. Is the proportion of men who pass Stat 200 different than the proportion of women? And we'll say, like, men was P1, that proportion, and women were P2. And if P1 minus P2 were negative, this would imply that men pass at a lower rate, and maybe I could make some decisions and try to focus on the guys more and, bother them more about doing their homework, for example. So there's an example to statistics, like a class I'm teaching, but here's another one. This is much more real life, like, is the proportion of subjects who take a drug and recover greater than those taking a placebo? As in, is your drug working? If you give your drug to 100 people and you give a placebo to 100 people, do the people in the placebo group do more of them, the people in the drug group do more of them end up recovering? So that's the kind of stuff where you'll care about two different proportions. And in general, the process for testing the difference in two population means is quite similar to one parameter. There's just a few extra steps and some small differences. So the first thing is that the standard deviation or standard error that we're going to use is found using this formula. So we have P1, 1 minus P1 over N1, plus P2, 1 minus P2 over N2. So that's what we used for standard deviation in the previous chapter. But the thing here that's a little bit funny is we are going to assume in the null hypothesis that P1 equals P2, that these proportions are the same. So we're going to have to find the sort of, I'll call it the average in quotes, of our P's to put into that formula. And that is the second difference. You have to find the null value of the proportion. So you're always assuming that P1 equals P2 in your null hypothesis. And this means you've got to think about how to find the average value of P1 and P2. And the reason that average is in quotes there is because these sample sizes could be different. So you have to find the average using this following formula that kind of weights for that. So here's the formula, and I'll tell you 2 ways to find it. So the first one is to take N1 times P1 hat plus N2 P2 hat all over N1 plus N2. Another way to think about that is think about this as what I'm going to call X1 plus X2 over N1 plus N2. And think about that recovery example. Number who recover on drug is this X1. X2 is the number who recover on placebo, divided by total sample size. So the numerator of this expression is the number of people in both groups who recover or who pass or whatever, divided by the total sample size between the 2 groups. And these formulas are equivalent, and they only won't match because of some rounding error in your P1 hat and P2 hat. So is the proportion of men who write a shopping list before going shopping less than the proportion of women who do so? We're going to let P1 and P2 represent the population proportions of men and women, respectively, who use shopping lists. And suppose we take a random sample of 50 men, 50 women, and they're asked if they use a shopping list when they have more than 10 items to buy. And of the 50 men, 20 said yes. Of the 50 women, 30 said yes. So show all 5 steps of the hypothesis testing procedure. And I'm going to add in a step 0, which is to find the sample proportions and then find the null value. So the proportion of men who make lists in our sample was 20 out of 50. And for women, this was 30 out of 50, or 0.6. Now the question is if these 2 things are equal, what's our null value? Well, we're going to call that P, and this is number in sample 1 plus number in sample 2 over N1 plus N2. So the number who made lists in the men's sample was 20. Plus women's sample, there were 30 out of 50 plus 50. So this ends up equaling 0.5. Now the reason that ended up being the average of P1 hat and P2 hat is because those sample sizes were equal. Had that not been the case, this wouldn't be true. Your step B is to find the null and alternative hypotheses. So the null hypothesis is that there are no difference in the proportions who make lists. So the proportion of men who make lists is equal to the proportion of women who make lists, or P1 minus P2 is equal to 0. HA specifically is that men make lists less frequently. So P1 is less than P2, or P1 minus P2 less than 0. So the proportion who make lists is the same. Proportion of men making lists is less than women. Next, let's summarize the data into an appropriate test statistic after first verifying that the necessary data conditions are met. Well, since our sample sizes are the same, we just have to do this for one of them. NP naught will be 50 times that null value of 0.5, which is 25, so check. And N1 minus P naught is 50 times 0.5, which is also 25, so check. If your sample sizes were different, you would have had to do this for both of them, but both sample sizes are 50. Now, the Z statistic, this is your sample statistic minus your null value over the standard error of your null value. And this is where it gets a little bit weird. So your sample statistic is P1 hat minus P2 hat. Your null value is this P hat minus P hat over the standard error of P hat minus P hat. And it's this thing that you got to find is a little bit tricky. So the standard error of P hat minus P hat is equal to the root of P hat 1 minus P hat over N1 plus P hat 1 minus P hat over N2. And that is that formula above from the very top of your page, just with P hat plugged in. So in this case, we have root 0.5 times 0.5 over 50 plus 0.5 times 0.5 over 50, which comes out to be 0.1. And the thing that students often mess up is that in here, you have to use the null value, not the value of P1 hat and P2 hat, because you're assuming in your null hypothesis that those things are the same. Okay, so now plug in all you know. You have P1 minus P2, so that's 0.4 minus 0.6 minus, in this case the null value is 0, divided by 0.1, which comes out to be -2. All right, next let's find the p-value by comparing the test statistic to the possibilities expected if the null hypothesis were true. So what's the chances that we get a z-value less than or equal to -2? Well, using your table, this happens with probability 0.0228. Decide whether this result is statistically significant. Well, we have to choose an alpha. So if alpha is 0.05, then yes, probability this p is less than alpha, and the result is statistically significant. And your final step is to make a conclusion in the context of the situation. So we reject H naught in favor of HA. And in conclusion, the conclusion we make in context is that men make lists less often than women. And we could be specific. We say when shopping for more than 10 items. So let's do another example. On the basis of its biochemical properties, Finnish researchers hypothesized that regular use of the sweetener xylitol might be useful in preventing ear infections in preschool children. They carried out a study to test this hypothesis. In a randomized experiment, 165 children took a daily dose of the placebo syrup, and of these, 68 got ear infections. Another 159 children were given daily doses of the drug, and 46 got ear infections. Is this observed difference in infection rates large enough to conclude that using the drug reduces risk of ear infections in general? So first let's find the sample proportions, and then we'll find the null value of the proportion. So for the placebo, the proportion who got sick, we'll call that P1 hat, there were 68 out of the 165, so 0.412. For the drug group, well, 46 out of the 159, which is 0.289. So it appears that that is lower. Now let's find the null value, assuming that these are the same. x1 plus x2 over n1 plus n2. Well, the number, so x1 plus x2 is the number who got ear infections among both groups. So 68 plus 46 divided by the total number of subjects, 165 plus 159, which comes out to be 0.352. Next, determine the null and alternative hypotheses. So H naught is that there is no difference. So P1 equals P2, or P1 minus P2 is 0. So proportion getting ear infections is the same. Proportion getting ear infections is the same. And HA is that P1 is greater than P2, or P1 minus P2 is bigger than 0. And P1 is our placebo group. So proportions getting ear infections is greater for the placebo group. That's what those are saying. All right, next let's find the test statistic after first verifying that the data conditions are met. Well, geez. Okay, well we would need to take n1 times that null value of p naught. So 165 times 0.352, and n1 times 1 minus p naught, 165, 1 minus 0.352. So 165 times 0.352, that's 58.08. This next one is 106.92, so check those are good. The other group is a quite similar size, but anyway, N2 P naught 159 times the same thing, 0.352, 55.968, N2 1 minus P naught 159, 1 minus 0.352. And that's also going to be big enough. 103.032. Okay, so check, big enough. Whew. Right, the more important bread and butter is getting this test statistic. So our Z statistic is P1 hat minus P2 hat minus P hat minus P hat, which is your null value, over the standard error of P hat minus P hat. So let's find that standard error of P hat minus P hat. So remember that's root P hat 1 minus P hat over N1, P hat 1 minus P hat over N2. And our P hat is that 0.352. 1 minus 0.352 is 0.64. 0.48. And my N1 was 165. And same numerator over N2, which is 159. And that comes out to be 0.05307. All right, so now our Z value, our P1 hat was 0.412 minus 0.289 minus 0 divided by this standard error. This comes out to be 2.32. All right, find the p-value next. So since our null alternative hypothesis direction is a greater than, we want to find the probability that we get a z value bigger than or equal to this 2.32. So we're looking at this bell-shaped curve. What's the chances we're there or bigger? Well, our curves only go to the left, so we're going to do probability z is less than or equal to negative 2.32. This is the fastest way. You could also do 1 minus probability z less than or equal to 2.32. That also works. If you want to do it and check, that's totally fine. This comes out to be 0.0102. Okay, part E, tell me whether this result is statistically significant. So let's take alpha equals 0.05, and we'll say yes, as our p-value of 0.102 is less than 0.05. The result is statistically significant. And make a conclusion. So, well, we reject H naught. And accept HA. And we conclude that the proportion of children who get an ear infection while taking, spell it right, X, is lower than those on a placebo. So the last thing we're going to talk about is how sample size can affect statistical significance and whether or not something has practical importance. So the first thing is that when there's a small to moderate difference between the null value and the true population value, a small sample has little chance of providing statistically significant support for the alternative. This is actually a problem with elections. So there might be a small difference between the proportion who support a candidate and that in your sample, because things are pretty close to 50-50 all the time. And so because that difference is so small, it can make it hard to draw conclusions that are accurate. And with a large sample, even a super small but unimportant difference between the null value and the true population value may be statistically significant, but may not really mean anything practically. So there's a study that's been done recently about eating meats and cancer, and that also was a very small difference that people said it was technically statistically significant. So to illustrate this example, let's look at something with a small difference and look at whether or not something is significant for two different sample sizes. So suppose you have a taste test and you're testing two drinks. We want to know if participants like drink A better than drink B. And we had 55% like drink A better than drink B. Let's find the test Z statistic and the p-value if the sample sizes were as follows. So our Z statistic is p hat minus p naught over standard error of p naught. And standard error of p naught is root p naught 1 minus p naught over n. So in the case of n equals 60, we have root 0.5, 1 minus 0.5, that's coming from our hypothesis here, over 60, which gives us 0.06455. Now our Z statistic is what we had, 55% like drink A better, 0.55, minus the null value of 0.5, all divided by the standard error, 0.06455, which comes out to be 0.77. And that should already say not unusual. This sample is only, well, less than a whole standard deviation above the mean, not strange. Probability Z is bigger than or equal to that 0.77. Same as probability that your Z is less than or equal to that negative 0.77, which is 0.2206. And in this case, you would fail to reject H naught. All right, so Z value, P value, conclusion. So what this is saying is if you have a drink and the population proportion who support is about 50-50, having a sample where 55% like one drink better than the other is not going to be all that strange. What if you increase your sample size to 960? What will change here is the standard error. So 0.5. 1 minus 0.5, but now it's over 960, which will make this a lot smaller. Comes out to be 0.0161. And your Z-score now is 0.55 minus 0.5 over 0.0161, which is 3.1. And a warning bell should go off that, hey, yeah, 3.1 standard deviations above the mean. This is unusual. Probability that Z is bigger than or equal to 3.1 equals probability Z is less than or equal to negative 3.1, which is 0.001. So in this case, you would reject H naught. And the kicker here is that you have a 5% difference is significant. And I mean, if you replace the drinks with elections or political parties, this is kind of what happens in real life with polling and stuff. Now that 5% difference might not actually be that important if you're like running a grocery store and stocking drinks. Maybe half and half is good enough. But if you're in a very, very, very big city and you're stocking drinks at a very, very, very big grocery store, then maybe you do want to buy more of drink A than drink B. Perhaps. And the final thing we'll discuss is practical importance versus statistical significance. So that phrase, statistically significant, just means that the data are strong enough to reject the null hypothesis. A result that is statistically significant like using a statistical meaning does not really mean that this is significant in the real world. So sometimes a result that is statistically significant does not have very practical significance. Is this more likely to occur when the sample size is very large or very small? So the practical significance would mean that there's not really a big or meaningful difference. Just in life. And the kicker here is that large samples can detect small differences. So there was an example early on in your textbook about a risk of was an error made by air traffic controllers. Had doubled. And the thing is that the baseline risk was quite low, or baseline error rate. And what this kind of amounted to is that maybe there were 5 errors one year and the next year there were 10. And sure, that did double, but that would be out of, say, many samples and really doesn't have any practical significance. One other possible problem in hypothesis testing is that you failed to find a statistically significant result even though the null hypothesis is false. So what will happen here is that you fail to reject H0, even if you should. And the previous example 7 that we looked at, this is much more likely to happen with small samples. As the standard error of P0 is larger, which leads to smaller z-scores.